A Peregrine Falcon hits 240 miles per hour in a nosedive. That is faster than a Formula One car at full throttle. And it does this with a body the size of a wine bottle, no engine, no fuel, just feathers and physics. Here is the part that should stop you cold. At that speed, the air itself becomes a weapon. Friction alone should cook the Falcon alive. So why does it land perfectly on a pigeon instead of disintegrating on the way down? This is not a quirk of nature. This is nature solving an engineering problem that our best aerospace teams still struggle with. And once you understand how the Falcon does it, you will never look at speed, air, or your own body the same way again. Let us start with what speed actually means at the boundary between you and the air around you. Right now, sitting still, air molecules are hitting your skin about 475 meters per second. You do not feel it as heat because the collisions are equal in every direction. But the moment you move through air at high speed, you are ramming into those molecules from one direction. They cannot get out of the way fast enough. They pile up, they compress, and compressed gas heats up. This is not metaphorical. This is the same thermodynamics that makes a bicycle pump warm when you fill a tire fast. At 240 miles per hour, that heating effect on an unprotected surface would raise skin temperature by tens of degrees in seconds. Exposed tissue would blister. Eyeballs would dry out in under a second. This is exactly why jet pilots need pressurized cockpits, visors, and full face masks. The Falcon has none of those things. What it has instead is something engineers spent decades trying to reverse engineer. Its feathers interlock with a precision that would embarrass most industrial manufacturing. Each primary feather on the wing overlaps its neighbor with a tolerance of fractions of a millimeter. When the dive begins and airspeed climbs past 100 miles per hour, the feathers do not flutter. They lock down. The whole wing surface becomes rigid, almost like a cast carbon fiber blade. Aeronautical engineers call this passive aeroelastic tailoring. The Falcon evolved it over 60 million years. We started understanding it about 40 years ago. But the feathers are only part of the story. The Falcon's skull shape is the real revelation. Most birds have a relatively flat face. The peregrine has a pronounced supraorbital ridge, that bony shelf above the eye socket, angled at a very specific geometry. Wind tunnel studies showed this ridge deflects airflow around the eye with almost zero turbulence. The eye stays moist. Vision stays sharp. The Falcon can track a target through a 240 mile/hour descent with better acuity than a human watching television from 6 feet away. And now here is where it gets genuinely strange. The peregrine's nostrils contain small bony tubercles, tiny cone-shaped protrusions inside the nasal passage. For decades ornithologists thought they were for filtering air. Then aerospace researchers noticed the same structure inside the air intakes of the Rolls-Royce engines on the Concorde. Those cones slow down the incoming air before it reaches the compressor so the engine does not choke. The Falcon does the same thing for its own lungs. At 240 miles per hour, uncontrolled airflow into the lungs would rupture the alveoli. The bony cones create a controlled deceleration of the incoming air. Nature solved jet engine inlet design before humans knew jet engines were possible. If this is blowing your mind right now, subscribe. Every single week we cover science like this. Real physics, real biology, the kind of stuff that makes textbooks look like they were written to put you to sleep. Now here is the second layer that most people miss entirely. The Falcon does not actually dive straight down. It spirals. Subtly, almost invisibly, but it spirals. And that matters enormously. A straight vertical dive means the prey sees the incoming shape growing larger directly in front of it. A spiraling approach keeps the Falcon at a nearly constant angular position in the prey's visual field. The way a car on the highway that is slowly overtaking you seems almost stationary before it suddenly rushes past. The prey's motion-detecting neurons do not fire the alarm signal because the Falcon is not triggering the rapid angular growth cue that signals incoming threats. The Falcon is essentially hacking the visual neuroscience of its prey using geometry. It is not just fast. It is surgically deceptive. And there is a third layer underneath that. The strike itself is not a collision. A 240 mile/hour full-body collision would shatter the Falcon's own skeleton on impact. Instead, the Falcon uses its hind talon like a scalpel swung at high velocity. The contact time is measured in milliseconds. The force is transferred in a focused point, not a broad surface. The physics here is identical to why a sharp knife cuts where a blunt one bruises. Pressure is force divided by area. By concentrating all that kinetic energy into one talon tip, the Falcon delivers a lethal strike while experiencing almost no rebound force itself. It is biomechanical judo at 240 miles per hour. What this means for the future is not trivial. Drone engineers are actively studying peregrine dive profiles to design faster, more stable unmanned aircraft. The interlocked feather structure is influencing next-generation morphing wing designs. Wings that change stiffness in real time based on airspeed without any moving parts or motors. The bony nasal tubercle has already been adapted in industrial fan blade design to reduce turbulence by 8% at high rotational speeds. That is not a small number. That is millions of dollars in energy savings per year in large ventilation systems. Every single system in that bird, the skull ridge, the feather lock, the nasal cone, the spiral approach, the focused strike, evolved independently but functions as one integrated hypersonic package. No committee designed it. No blueprint was drawn. 60 million years of trial and error converged on a solution that our smartest engineers are still only beginning to translate into human technology. The next time you see a bird, understand that you are looking at an aerospace vehicle refined across a timescale your brain genuinely cannot visualize. And it is hunting, right now, using physics that should be impossible, and surviving it flawlessly. If this episode changed how you see the world, subscribe and hit the bell. Next week we are going deep into something that will make this look calm. You do not want to miss it.